video, we're going to take a look at a free response question from the AB 2023 exam. We'll be looking at number 4, which is analyzing the graph of f prime of x. In this question, they specifically ask for relative mins and maxes, concavity, limits, and they also ask us to really apply the fundamental theorem of calculus. And we can look at that two different ways, which is really going to be an application from the extreme value theorem. So let's go ahead and take a look at the question and see what exactly we're dealing with. And besides answering the question, we're going to go a little bit deeper to see what other questions they could ask, because you obviously aren't going to get the same question, but this is a very typical question in terms of free response questions. I would expect to see one involving graphs and most of these topics. So first, let's take a look at what they're giving us. They're giving us the graph of f prime. So realize we're going to be interpreting the graph of the derivative, but we're going to be asked questions about the function f. They're telling us it's a closed interval, so a lot of times that tells us what theorems might be applicable. So if it's continuous and differentiable, we have the mean value theorem. If it's continuous, it will have the extreme value theorem. And very important, they're giving us a value on f. They're giving us the value at 2, so not f prime, so we'll use that somewhere. A lot of times that gets missed, so good to circle that. And they also tell us that we have 2 line segments in a semicircle. That means we're going to be able to find area or values at certain points, so we want to keep that in mind. So part A is going to ask about a relative min, max, or neither at a particular point. Part B talks about concavity, so we want to understand concavity as well as points of inflection. Part C, they managed to sneak in a limit question, so that usually tells me we're going to need L'Hopital's rule, so they can test you on that. And then part D, what I call the money question, they're looking at the absolute minimum. And we typically are thinking extreme value theorem when we talk about an absolute minimum. And that means we'll probably have to apply the fundamental theorem of calculus because they're giving us f prime, not values of f. So let's go ahead and take a look at part A and see what exactly we're dealing with. So here, we're looking for a relative min, max, or neither at a particular point. So let's just take a look at this part first. So at x equals 6, we're right here. So I like to set up a sign chart right away, regardless. So x and f prime, this is just a good habit to have. So we're looking at x equals 6, f prime, and again, this is the graph of f prime, so we're looking at the value. At 6, f prime is 0. So what we want to do is look before that, we'd see f prime is always positive, and after that, f prime is still always positive. So we do not have a change in sign. So we have f prime is greater than 0, f prime is equal to 0, f prime is greater than 0, and this is at x equals 6. So that means we have neither. So what we would want for a minimum, we'd want to see a sign change going from decreasing, from negative to positive. So the function's decreasing to increasing. And a maximum is the opposite. We'd be going from increasing to decreasing. So let's just go ahead and take a look at analyzing each point. So where is f prime 0 or undefined? So that's where we find mins and maxes. So this is the idea that they're testing you on. And on this graph, we can see x equals -1, x equals 2, and x equals 6. The value is all 0. So I'm just going to go ahead and make a quick little sign chart here. On x, we'd have -1, we'd have 2, and we'd have 6. And it's not undefined anywhere, so we would look for breaks or anything like that. The fact that f prime is continuous tells us that f is also continuous and differentiable. So f prime here, we would have 0, 0, and 0. And to the left, again, we have positive values. We're looking at the values. To the right of -1 and left of 2, we see that it's negative. And in between 2 and 6, as we saw before, it was positive, and to the right of 6 is positive. This gives you an idea of what f is actually going to look like if you think about it. We're going to do like mini slope lines here. So we see it's increasing, it's 0, it's decreasing, decreasing, 0, increasing until it reaches 0, and then increasing again. This gives you an idea of the graph of f that's a lot of times you can kind of smooth out. If you ever have to do any curve sketching, we can kind of see what's going on. So there is our graph of f, more or less. All right, on to part B. Part B is asking us about concavity, right? So let's just look at what concave down actually means on F. So if this is F, this would be concave down. So concave down tells us we have a positive slope, we have a zero slope, we have a negative slope. Or really, we can look at any piece of this and we just see that slope is decreasing. That's really our definition of concave down. Slope is decreasing. So we are given the graph of f prime. We are given the graph of the slope. So we want to know, where is this graph decreasing? So to interpret concave up and concave down on f prime, you just look for increasing, decreasing. And again, they're talking about open intervals. This means we're not going to include any endpoints on our interval when we define it. So we see here we're starting at -2 and we're decreasing until we reach x equals 0. After that, it's increasing till we reach +4, and at +4, we are decreasing until we reach x equals 6, and then it's increasing again. So the answer for this problem is quite simply -2 to 0 in union with 4 to 6. And our reasoning is f prime is decreasing on those intervals. So there's our justification. Some other things that may be asked for in the future is points of inflection. So a point of inflection occurs on f prime. They're mins and maxes on f prime. So a min or a max on f prime, because you can see that's where it changes concavity. So our first actual change from decreasing to increasing, our relative mins and max, would be at x equals 0. So at x equals 0, we would have a point of inflection. And then again, we have another min or max here at x equals 4. It's changing from increasing to decreasing. So let's write those down. So at x equals 0, x equals 4, and even at x equals 6, that's a very important point of inflection. We're going from decreasing to increasing. And we're not going to consider the endpoints because we don't know what's happening after that. So if we were asked for points of inflection, we do know how to find that. And we also know how to find concave up where it's increasing. Part C, they throw a limit question at us. So we're just going to typically think L'Hopital's rule, but let's just go back to the basic idea of limits. So the first thing we want to do when we see a limit as x approaches 2 is we're going to plug in to see if we can get a value. And we're allowed to plug it in for functions if functions are continuous. And we do know f of x is continuous, and all these other functions, linear and quadratic, they're also continuous. So we're just going to go ahead and plug that in. So we're going to implies 6 times f of 2 minus 3 times 2 all over 2 squared minus 5 times 2 plus 6. And this is where we have to use f of 2. We know f of 2 is 1, so we can do that. It goes to 1. So this is equal to 6 minus 6 over, we have 4 minus 10 plus 6, so we get 0 over 0. This immediately tells us, all right, we have the indeterminate form. So that means L'Hopital rules apply. L'Hopital's rule applies. You can also apply L'Hopital's rule, other indeterminate forms, but you do want it as a ratio of a numerator to a denominator. So that means it's going to be equivalent to taking the derivative of the numerator, which is going to be 6 f prime of x minus 3 over the derivative of our denominator, 2x minus 5. Remember not to confuse L'Hopital's rule with quotient rule, all right? Very different. And now we can go ahead and find these values. So that's going to lead us to 6 times f prime of 2 minus 3 over 2 times 2 minus 5. And we have our graph here, so we can see f prime of 2. Here is 2. Again, we're looking at the value because it is f prime. F prime of 2 is 0. So we'd have 6 times 0 minus 3 over 4 minus 5. So we get -3 over -1. So our final answer is +3. On to part D. Part D. Notice we're looking for the absolute minimum value. Immediately when you see that, you're thinking extreme value theorem. And we're given a closed interval of -2 to 8, and we have to justify. So things I want you to consider right away when you see extreme value theorem, make sure you write down endpoints. I mean, we can kind of talk our way through what the answer is, but we're looking for consideration at least of the endpoints, so x equals -2 and x equals 8. And then it also states that an absolute minimum or maximum can occur when f prime is 0 or if it's undefined. So in our case, it is equal to 0 in 3 places: at -1, here we go, at +2, and again at 6, which we looked at earlier. Again, we can kind of talk our way out of some of these, but let's kind of figure out what we think the answer should be. So earlier we looked at the idea of where the zeros are, and we know what the graph is, and we sketched that out. So we kind of have that idea already, but let's look at the idea of finding area. So we can see we start at some point at -2, and we're accumulating positive area. So we're going up till we reach 0. Then we're accumulating the same amount of area, but it's underneath the axis, so it's negative. And then we're accumulating more negative area, so we're going down till we reach -2. And after that, we're just accumulating positive area. So we're going to be increasing till we reach 0 and increasing again. So we can already see that our answer is going to happen at x equals 2. But things we have to consider, we have to truly justify this, and we're looking for the value. So we're going to have to find the value. So let's just talk about what we really want to do with this. So in terms of the theorem itself, we should set up a little chart here, a little table. What are we looking at? We're looking at -2, -1, 2, 6, and 8. And we're going to be able to discount some of these. So we already know at 2, this is very important, we had that value, f of 2 is 1. So at 2, we already know the value is 1. And we're just going to compare values and see, what's our smallest value? What's the absolute minimum? Now, we can explain away 8. 8 we can kind of take off the table here. We can find it just in case. But we can talk about the fact that we are accumulating positive change. So accumulating f prime greater than 0, so it can't be a minimum. That implies we're going to have, some kind of relative maximum or a maximum or an absolute maximum. We have something else going on. It's not a minimum. That's all we know, not a minimum. And again, at 6, we saw earlier that it was a point of inflection. We didn't mention that earlier, but we mentioned the fact that it's neither a min or a max. So we can refer back to there. So it's neither a min or a max. Min or max. And at -1, we can eliminate that also, because we can say that f prime goes from positive to negative, f prime from greater than 0, f prime less than 0, and it's 0 there. So this indicates that we have a maximum here, a relative maximum. So really we're concerned with f of -2. That's what we need to find, and we can find the others if we wanted to. So what we're going to look at is the fundamental theorem of calculus as an accumulator. That tells us that the value you're looking for equals to the value you started at plus how much change you've accumulated over that interval. And we have to consider whether it's positive or negative. So in our case, we want f of -2 will equal f of 2 plus, and this is important, we're going from 2 as our old one, our starting point, up to -2, even though that's out of order, f prime of x dx. Now, we don't like going backwards a lot of times, and we can get confused in the graph. So let's rewrite this and switch the limits of integration. And remember, if you switch the limits of integration, our sign changes, so we now have minus, and that's from -2 to 2 of f prime of x dx. And we know f of 2 is 1, so now we're going to subtract some value. So we're going to go back up, and let's just take a look at that area. Let's go ahead and erase what we have here, and let's go ahead and take a look. So from -2 to 1 to -1, we can see that we have positive area, but from -1 to 0, we have that same area. So they cancel out, so we don't even need to look at that. But if we had to, we can see here we have +1, and over here it's under the axis, so we'd have -1. So we're just looking from here to here. So from 0 to 2, and then 0 to -2. So we can see that this area in here, and we can write that out as 2 times 2 divided by 2, which is just 2. So this would be a -2. So the area in question over here is 1 minus 1 minus 2. So we end up with 1 minus, and then we'd have negative 2. So we have a value of 3. So we can go back to our chart and say 3. So by the extreme value theorem, we can see that the point 2, 1 is where it occurs. So the way you would write this down is you have an absolute minimum of, and then what that value is, the value was 1, and it happens at x equals 2. So that's that answer right there. But now, I'm concerned with other applications. What if you had to find the absolute maximum or something else like that? Let's go ahead and figure out what the value is at 8. What is f of 8? So f of 8, by our theorem, would equal f of 2 plus the integral from 2 to 8 of f prime of x dx. So here we can see that f of 2, we knew that was 1. Now let's go ahead and we have to break this shape up. So from 2 to 4, we can see we're going over 2, up 2, so we have that area. So we're going to have 2 times 2 divided by 2 again. So we have 2, so it's going to be plus, that's an area of 2. Now, our area under the semicircle, notice we have a rectangle, but we'd have to subtract out the semicircle to actually find out what these values are. So this rectangle here is 4 to 8, so that's 4 with a height of 2. So you would have the rectangle is 8, and just so you picture that, you have the rectangle, and then you're subtracting out the semicircle. And the semicircle has a radius of 2, so we would have pi times the radius squared divided by 2. So we'd have 4 pi over 2, and we end up with 2 pi. So we end up with 8 minus 2 pi. And make sure I have that right. And we have plus, here we go, plus 8 minus 2 pi. And this brings us to 1 plus 2 plus 8 minus 2 pi. So we'd have 11 minus 2 pi. And you can always approximate, that's basically 2 times 3 is 6, so we have about 5. But obviously we can actually find this value if we needed to, 11 minus 2 pi, and we can do the same for the rest of them. I just thought it was important that you look at the idea of how to deal with semicircles and finding another area and looking at relative mins and maxes. So I hope that helps, and I hope you do well in the exam.